Okay. So, good evening, everyone. My name is Chandan Kumar Gupta.
Good evening, sir.
Good evening, Ashok. Good evening, everyone. My name is Chandan Kumar Gupta. I'm a research scholar in Department of Mathematics, IIT Patna. I am your prmf NPTEL TA for the course Probability and Statistics. This course is offered by Somesh Kumar. He is a faculty in Department of Mathematics, IIT Kharagpur. Okay. Anyone wants to introduce himself or herself? Anyone? Okay, let me share the screen. Okay. Is the screen visible?
Yes, sir.
Yes, sir. Yes.
Okay,
Yes, sir.
okay, thank you. Okay, so we will start now. Okay, this is your second week course. Sorry, second week of the course. Okay, and in previous week we have learned about the ring field, sigma ring, sigma field, and introduction to probability and much. Okay, so we will have a recap of the first week. Okay, we will start from the introduction to probability. Okay, what is the probability? Anyone? Can anyone explain the meaning of probability? Okay, let me explain then.
Possibility.
Yeah, possibilities or chance of occurring anything, any event, happening of anything. Okay, there is some probability, some possibility, or some chance to occur. Like it may possible today, like it may rain or it may not rain. Okay, so there is a chances, there is a possibilities that it will rain. Okay, today, tomorrow, or any day. So probability is defined as the chance of occurrence of any events. Okay, so we will start from the terminology that are used in probability. So like experiments, we will talk about the experiments all the time, like random experiment. Okay, we perform an experiment and what is the probability that that event occurs. Okay, these type of questions we are going to deal with. So experiment is what? Conducting something in certain condition which results in some outcomes. Okay, when we do something, okay, that have some outcomes associated with that experiment. Sorry, that what we have done or what we are going to do, that is called experiment. There are mainly two types of experiment, like deterministic experiment and random experiment. Okay, deterministic means sure and certain type of thing. Okay, the experiment which have only one outcome means we are 100% sure that when we perform this experiment, we got the outcome as a particular outcome we will get, and that outcome is sure, certain. Like tossing a coin with same face on both sides, like biased coin. When we are tossing a biased coin, then the outcome that head occurs is one, because both the side has a head. Like experiments related to physics, chemistry, these are also the deterministic experiments. And in here we are going to deal with random experiments. Okay, and what is a random experiment? Random experiments are like when we perform the experiment, okay, we have some outcomes, we have certain outcomes, like either this or this or this happens, but we are not sure that which outcome occurs in that particular trial. Okay, like tossing a coin, rolling a die, drawing a card from a deck of cards, these are the random experiments. We know that suppose when we roll a die, we know that there we will surely know that either one or two or three or four or five or six will occur, but we are not sure that at a particular roll what will come. Okay, so this is the random experiment. Okay, and we are going to evaluate, actually we are going to evaluate the chances that that outcome occurs or not. Okay, this is our motto, this is the probability actually. Some other basic terminologies like outcomes. Outcomes are possible results of an experiment. Sample space means set of all possible outcomes. Like why? Like suppose we roll a die, then the possible outcomes are 1 to 6. Okay, we have got either 1 or 2 or 3 or 4 or 5 or 6. These are the sample space. Okay, like 1, 2, 3, 4, 5, and 6. Okay, no other outcomes, no other elements occurs other than 1 to 6. Okay, events are actually the set of outcomes of an experiment to which probability is assigned, like what we are interested. Like suppose we roll a die and we want to get an even number. Then the event is like a 2, 4, 6. It is a subset of sample space actually. So event is a subset of sample space. All the subset is actually an event of that sample space. Okay, and there are different kinds of events, like mutually exclusive events, which is also called disjoint events, exhaustive events, independent events. Okay, so mutually exclusive events are a kind of two or more than two events actually are said to be mutually exclusive when event A and event B are mutually exclusive when there is nothing common in between. Okay, am I audible now?
Yes, sir.
If anyone want to ask anything, they may directly ask. Okay, they may interrupt me in between and ask. Okay, now exhaustive events. Exhaustive events are those events whose union equals the sample space. Like the set of events whose union covers the entire sample space is known as exhaustive events. Okay, like here set of even number, and suppose we have assigned set B as set of odd numbers. Then A union B equals S, sample space. Then A and B are said to be exhaustive events. Okay. Or independent events, like as name suggests, it is independent from the other events. An event is independent from the other events or the previous events. Okay, like events which are not affected by the occurrence of other events. Okay, like uh, suppose we toss a coin. Okay, uh, and in first we get head. In first toss we get head. What is the chance that in second trial we will also, it may possible either head or tail occurs na? In third also. Okay, so this is independent case. Now definitions of probability. We are going to define the probability actually. How many definitions are there? Anyone know?
3.
Three. And which one? Name them.
Classical definition, anxiety definition, statistical definition.
Exactly. Classical definition. This was given by Laplace in 1810 actually. Okay. This definition is the ratio of the favorable and total outcomes. Okay, the favorable number of outcomes and total outcomes, these ratio gives the classical definition or probability of the that event. Here, like suppose, and also here three conditions must satisfy. First one is mutually exclusive, means two or more than two events are mutually exclusive events. Exhaustive and equally likely. What is the meaning of equally likely? Anyone?
Having equal possibilities.
Yes, having equal probability to occur that event. Okay, equally likely events. Okay, like getting head or getting tail, both have the probability 1 by 2, which is also probability of getting tail in tossing a coin. Okay, so head and tail are equally likely events. Okay, and this is the probability. Also, we know that the probability lies within 0 to 1, including both. When probability equals 0, probability of an event equals 0, this is called impossible event. And when probability of any event equals 1, it is called sure or
Sure
certain
event.
event. Okay, sure or certain events. Okay, also there are also, these are always positive. Okay, these the bounds of probability is 0 to 1, and many more properties are there. Okay, and drawback of the classical definition is n needs to be finite and assumptions of equally likely events. Okay, now the second one is statistical or empirical definition. In this definition, we have taken the limit of the outcomes. Like if n trials an event E happens m times, then the probability of happening of event E is given by this formula. It has also limitation, like it may possible that limit may not attain or does not exist. If an experiment is repeated a large number of times, it is also possible that the same condition is not possible to like remain on this continue the experiment on the same situation or same conditions. So this is the statistical definition, and this is the drawback. The third one is axiomatic definition. Axiomatic definition is actually uh, it is based on three axioms. Okay, the first axiom is like this: probability of any event lie within 0 to 1. This is non-negative property. Okay, second property is like probability of sample space equals 1, and the third is if a1 a2 up to infinity is a countable sequence of mutually exclusive events. Mutually exclusive means ai intersection aj equals 5. Okay, so in that case, probability of union of ai equal to k, this is misprint, equal to summation of probability of ai. Okay, if events are mutually exclusive, if not, then this third axiom is not satisfied. Okay, so this is the axiomatic definition of probability. Okay, now those are actually week 1 content. Okay, now from here we start week 2 content. Okay, in week 2 we are going to discuss about the conditional distribution, not conditional distribution, it's conditional probability, multiplication rule, Bayes theorem, and then independence of events, then random variables, and then probability distribution, CDF, and the properties of CDF, and the discrete types of random variables like discrete, continuous, and mixed random variable. Okay, and then we will going to solve questions related to these topics. Okay, so start from conditional distribution. Sorry, conditional probability. Conditional probability is actually based on conditions, like when we evaluate probability with certain conditions. Suppose we draw like for example, okay, let first probability of a given b. This is the representation of conditional distribution, like probability of event a given that b has already occurred, and then we need to evaluate the probability of a. This is equals number of probability of a intersection b and divided by probability of b. The given condition is always in denominator part. Okay, this may also be written as number of elements in a intersection b, number of elements in sample space, and whole divided by number of elements in b, and then number of elements in S, which is simplified as number of elements in A intersection B Number of elements in B. Here we see that actually, like when we deal with the conditional probability, okay, our main focus is on the given condition, like here B. We are much interested in focusing on the already occurred event and not on sample space. Okay, so first first we will sorry first we want to focus on number of elements in the conditional, like the given condition. Okay, like for example, suppose we roll a die. Okay, and already we know that 1, 2, 3, 4, 5, and 6 are the outcomes. Okay, this is the sample space, and we say event B as either odd number or prime number. For example, odd number or prime number 1, 2, 3, 5. Okay, and now event A, we will define event A. Then what is the probability of getting an even number when it is given that the we have a already prime or odd number occurs? Okay, then what is the probability of selecting an even number when we know that a prime number already occurred? Okay. In that case, suppose uh, in that case, probability of A given B. What is the probability? Here 1 and here the total is 4. Because in A intersection B, in A intersection B, A is even number, na? 2, 4, 6. Okay, A intersection B has only 2 as a common element. Okay, and in B there are total 4 elements. So this is the conditional probability. We will discuss about this with numericals. Okay, now multiplication rule. And what is multiplication rule comes from here as well. Probability of A given B equals probability of A intersection B upon probability of B. From here on, when we multiply this, we get probability of A intersection B equal to probability of A given B into B, or probability of B given A into A. Because probability of like A intersection B equal to probability of B intersection A, na? A intersection B equals B intersection. Intersection is commutative in nature actually, that's why. Okay, we can write either this or this, both are same. Okay, and for generalization purpose, like probability of intersections of AI equal to probability of A1, probability of A2 given A1, probability of A3 given A1 intersection A2, and probability of like A4 given A1 intersection A2 intersection A3, and then so on. Okay, up to n, if we have n outcomes or n events are there, then an is intersection from a1 up to a2 to an minus 1. Okay, this is the multiplication rule of probability. Okay, when we are given, these are actually all used in calculation part. Okay, now Bayes theorem. Okay, anyone know about the Bayes theorem? Na? Everyone know, I think. Okay, let E1, E2 up to En or are pairwise disjoint and exhaustive events. We need to focus on this actually. Okay, when events E1, E2 up to En are pairwise disjoint events and exhaustive events. Okay, then probability of EI given A, this is calculated with the help of probability of A given EI into probability of EI and summation of the same for all I. Okay, so here we see that like in Bayesian, in Bayes theorem actually, in Bayes theorem, we are given prior probabilities. Prior probabilities are given and we need to calculate posterior probability. we need to calculate posterior probability. Okay. Uh, for this, we are also given a likelihood. Likelihood event are also given, which is common in all EIs. Okay. So we are E1, E2 up to n number of events occur, which are pairwise disjoint and exhaustive events. Also, uh, uh, and also an event A, which is likelihood event. Okay, which is likelihood event. Okay, so we want to calculate the probability of that A had already occurred, and what is the probability that A has occurred for the particular EI group, and this can be calculated with the help of this formula. Okay, in Bayesian, actually in Bayes theorem, we will need to focus on what are the outcomes. Sorry, what are events, like what is E1, what is E2, what is E3, and what is A in the question. We will discuss this later. Okay, and now the independent event. Okay, in independent event, actually two events are said to be independent event when A intersection B. Then the probability of A intersection B equals probability of A into probability of B. Suppose we want to check whether the given two events are independent or not. We must find out the probability of A intersection B and the probability of A and then B, and check whether this condition holds or not. Suppose we are given three elements, for example, events A, B, and C. In that case, probability of A intersection B intersection C equals probability of A into probability of B into probability of C. Then this is called independent event. Okay. Also, if for given three, probability of A1 probability of A1 intersection A intersection B equals probability of A into probability of B. Then this is called pairwise independent. Okay. So when more than two elements are there, then when we consider two events at a time, then it is called pairwise if this condition holds. And if all holds, then is it called independent events. Okay. Now random variables. Random variables. Can I even explain what is a random variable? Anyone? Okay. Okay. Random variable actually, it is not a variable, first of all. Okay. Random variable is a function. It is a converter kind of thing, which convert what? Sample space elements. It converts sample space elements to a real number. Means it assign a number to all the elements in sample space. Suppose suppose we roll or we toss, like here already example is rolling a fair die of twice. Okay? Like suppose we roll a die twice, or we roll two dice simultaneously. Both have the same outcomes. Both have the same sample space. Okay, like this. Okay, here every element of S is suppose is related to a real number according to this random variable. So first we need to define a random variable. What is a random variable? First, it is a function which maps sample space element to a real number. Okay. Now, what is the like how the variable defined? Like suppose we can define like sum on both sides. Okay. Then we have outcomes like 2, 3, 4 up to 12. Okay. So every element of S is related to some number like either 2 or 3 or 4 or 12. Like 2, 6, 26 is a number which is related to x equals 8. Okay, so sample space element is assigned a real number, and that number is 8 here. Okay, like 6 1, it is assigned a number 7. So random variable is not a variable, it is a function. Okay. Now probability distribution. Okay, distributions is like want to distribute something like, okay, so probability distribution, we want to distribute the probability, okay, to whom, like x is a random variable, okay, and number of heads in tossing 2 coin is the example here. Like suppose when 2 coins are tossed, we get head tail, head, and tail. Okay, these are the outcomes. These are the sample space elements. Okay, so how to distribute the probability? So first here, let us define x equals like number of heads. Okay, so the possible values of x is either 0 or 1 or 2. Okay, so like for 0, okay, how probability is distributed? Is it like there are 4 elements like 4 by 3? It's like 1 by 3, 1 by 3, 1 by 3. Okay, suppose here probability are equally distributed. Okay, for getting number of heads, but it is not the case. Okay, like we want to distribute the probability on the basis of random variables, and here it is the number of head. So here number of head is 2, here 1, here 1, here 0. So on that basis, number of head is equal to 0, and it has a probability at 1 out of 4. Okay, and also for 1, number of elements is, there are 2 elements in sample space which have 1 as a head, 1 head. Okay, so that means 2 by 4, and that is 1 by 4. So we distribute the probability on the basis of this. We are not equally distribute the probability. We distribute the probability on the basis of the elements that are in sample space. So this is the distribution of probability. Okay, how probability is distributed within the elements of the sample space. Okay, now cumulative distribution function. It is also called CDF. And the formula for this is, it is denoted by fx, and the formula is probability that x is less than or equal to x. Less than or equal to. Okay. Like like in questions like when we deal with the ogive functions, we are calculating median, then there also cumulative frequencies are used. Okay. The same thing is there actually. Suppose probability that x equals, for that case, x equals 0 head, which is equal to 1 by 4. Probability that x equals to 1 head, it's 2 by 4. Okay, and probability that fx, okay, 1. For this, actually 1. This means probability that x equals 0 plus probability that x equals 1. This implies 3 by 4. Okay, all the previous probabilities also add. Okay, are summed in this CDF, cumulative distribution function. Okay, now the properties of cumulative distribution function is like it has 3 property mainly. Okay, suppose we are given a function and these 3 properties are satisfied, then we say that function is actually a distribution function. Okay, like limit x tends to minus infinity. Okay, we will check whether the the given, for given function like fx, like x. Okay, and we are given x belongs to 0 to 1. Okay, so we check for x here and here. This is the minimum value and this is the maximum value. Okay, so for here x tends to minus infinity. So at minimum value, the given value gives 0. Okay, the given function gives 0. Okay, or for maximum value, it gives 1. The first property is for limit x tends to minimum value of f of that function where that function defined, and the maximum value is 0 and 1 respectively. The second one is non-decreasing case. Non-decreasing is what? If we have selected two values x1 and x2 from the given domain, in that case the function values also satisfy this property, right? Fx1 either less than or equal to fx2. Okay, and the third one is limit of fx plus h equal to fx, that is right continuous at every point. Okay, for every point the function is right continuous. That means this condition, non-decreasing condition, and right continuous condition. These three conditions, if a function holds these three conditions within the given domain, then that function is called the CDF or distribution function. Okay, we will solve the question on the basis of this as well. Okay, now random variables, actually types of random variables. Okay, so there are different types of random variables, like discrete random variable, like continuous random variables, and the third one is mixed. Okay, discrete random variable is like the range of x is at most countable. Okay, when we define like a function like probability that x equals ncx p to the power x q to the power n minus x. Here x is defined as how? 0, 1, 2. This is countable. Okay, so this is the case of discrete random variable. Here x is discrete random variable. Okay. Also, when this x is defined like this, x belongs to 0 to 1 or something which is continuous, like not countable, in that case it is a continuous random variable. And mixed random variable is that random variable which has value at a particular point also in interval. So this is a mixed, means which is discrete as well as continuous both. Then that random variable is called mixed random variable. Okay, we have a question regarding this, I think. Okay, we will solve this.
Countable parts, sir.
Hello, hello. Yes.
Countable means what, sir?
Not. I'm not able
Countable.
to. Countable. Okay. What's your question actually? I can't hear it clearly.
Countable means what?
Oh,
Is the limits
count.
that before the infinity are to consider countable?
Like countable means we have a one-to-one map, na? In mathematics, we are discussing about the countable. Countable is, suppose for example, we are just define natural number. What is natural number? Natural number is what? Counting number is known as natural number actually. So we count from 1, 2, 3, 4 up to this. Okay. So it may possible, it may go to infinity. So countable means actually there is a one-to-one map. There is a one-to-one function. Okay. Like for every x here, for every x, there is a px. And there is only one px. 1-to-1 map is there. So it is a countable. Is it clear? Hello.
Okay, sir.
Okay. Okay. Now from here, we're going to solve the question. Okay. So first question is
Excuse
like,
me, sir.
yes.
Sir, example of mixed random variable, sir.
Okay, example of mixed random variable. Okay, I can, maybe I can write here. Actually, look, you people, I don't know whether you people know about the continuous distributions. Like suppose 0.8 e to the power minus x. For example, this is a given function. Okay, here x is actually mixed random variable. Okay, how? When you check like probability had three property. Na? Actually, I'm not yet discussed these things because it is not there as till now. Okay, suppose we know na, we know that the integral over is this equals 1. This is the property, one of the property of a function to be a PDF, a density function. Okay, so here when we imply this property on here, we get 0.8. So there, I think I need to write here something as well. Wait, I need to write the whole thing. X equals 0. Okay, am I writing correct or not? Actually, I don't remember exactly, but this is the example. Okay. Hello, Ashok. I think you have asked the question.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Actually, yes. Actually, what is going here? Na? Like we have a different properties for a function to be a density function. This is one of the property. Okay. So in continuous case, the probability at a point is 0. Okay. And in some examples, like I think here, when we get then when we evaluate this quantity, we will not get 1. So there is some point. At some point, the probability is not 0. That point is called jump point actually. Okay. So this x is now said to be a mixed random variable because here for continuous for continuous variable probability at a point is 0. But in that case, the probability at a point is not 0. So it is continuous as well as it is the random variable x is discrete or continuous both. So this is called the example of for a mixed random variable. Okay. I'm not clearly able to explain now, but this is the example actually. I remember the example like this. Okay. And here we see that the probability at a point is not 0. For here, probability at a point x is equal to 0 is not equal to 0. That means it is a discrete random variable. Also, for x is greater than 0, the probability within x, like for example 4, it is something. Okay. So for continuous or for discrete, for given function, discrete and continuous, both variables include can I say like probability at a point is there and probability in an interval is there. Okay, so it is a continuous and discrete both. So this is a mixed case. This type of example, I think next week we will discuss about the mixed example regarding to mixed random variable. Maybe if there is something in my slides, then we will discuss comprehensively. Okay.
Okay, sir. Thank you.
Okay. Okay. Now start with the question number 1. Here we are given B subset A. Okay. The probability like B given A is equal to what? So first, it is a conditional probability. So we know that probability of A given B equals probability of A intersection B upon probability of B. Clear? This is the general formula for a conditional distribution. Okay, we have given a condition here. Since B is a subset of A, okay, so obviously we will get A intersection B is what? Can anyone?
B.
B.
Equal B.
Probability of A given B into probability of B.
Probability of A given B. Okay. Probability of A given B into probability of B. Okay. You are saying right, but here we need to calculate or we need to equate A given B is equal to in some part. Na? So with the help of this condition, B subset A. Okay. We can write A intersection B equal to B. Na? Like this is A. This is B. B subset A. Okay. So B intersection A equal to B. So we can write probability of A intersection B equal to probability of B actually. So from here, probability of A given B is equal to probability of B whole divided by probability of B, which is equal to 1. Okay. So here we see that if B is a subset of A, then probability of A given B equals 1. Means it is already a subset of A, na, of event A. So the conditional distribution, the conditional probability is also given equals 1. Okay. Is it clear now? It is simple, I think. We need to check what is the question. You are telling right actually. But we need to use this concept, na? Like A intersection B equal to B, so that we can calculate the value of A given B. Okay. Okay, now question number 2. If two events A and B are independent, then probability of A complement intersection B complement is equal to. Okay, so how to proceed? Anyone? Okay, let's start. We are given A and B are independent. And for two events to be independent, this condition A intersection B equals probability of A into probability of B. This must satisfy. Okay, two events are said to be independent if intersection, the probability of intersection equal to the multiplication of their individual probability. Okay, so this we can write actually. Okay, now one more thing, like we also know that like probability of A complement intersection B complement equal to probability of A union B complement. By which law? Can anyone?
De Morgan's law.
De Morgan's law. Okay. De Morgan's law states like the intersection, and also we can write that the A complement union B complement equal to probability of A intersection B whole complement. This is also De Morgan's law actually. Okay. So with the help of this, we can write, we need to calculate this probability of A complement intersection B complement. Okay. So probability of A complement intersection B complement, this can be written as probability of A union B complement with the help of De Morgan's law. Also, we know that this can be written as 1 minus probability of A union B. Can we write this?
Yes, sir.
Okay, we can write this like if A is an event, then A complement can be written as what? S minus A. So in probability, probability of A complement equal to 1 minus probability of A. So probability of A union B complement can be written as 1 minus probability of A union B. Okay. Now probability of A union B, with the help of addition law, we can write this like 1 minus probability of A plus probability of B minus probability of A intersection B. Okay. And from here, 1 minus probability of A plus probability of B. Since we are given A and B are independent, so we can write probability of A into probability of B, because A intersection B can be written as A into B. Okay. Now from here, this can be written as 1 minus probability of A minus probability of B plus probability of A into probability of B. 1 minus probability of A minus probability of B, 1 minus probability of A. We will take common probability of B from these two. Okay. And we get this. And then 1 minus probability of A is common. And we get 1 minus probability of B. Okay. And 1 minus probability of A is what? Probability of A complement. And this is probability of B complement. So first, okay, there is a misprint here actually. So this option is correct, or this option is correct. Okay, is it visible now?
Yes, sir.
Okay. So here we see that na, like this is correct. Option 1 is correct one. Okay, probability of this can be written like this. Okay. Also, we see that probability of this can also be, it can also be written like this. So this option is also correct. And also this is a misprint actually. Here it is -1 minus probability of A actually. Okay, and 1 minus probability of B. So all the three options are correct. That means option D is the correct one for this question. Okay. We can write, if you don't like understand this, you will take the help of Venn diagram. With the help of Venn diagram, you may able to solve this as well. Okay. Draw A and B. And what is A complement intersection B complement? A complement and intersection B complement. This can be written as this is like this, na? And this is what? A union B, S minus A union B. So from here, you can write this. And from here, you can write this. And then just explain, just simplify. Or okay. Now, third question is like, given that probability of A equals 1 by 3, probability of B equals 1 by 4, and probability of A given B is 1 by 6. Then find the value of B given. Okay. Okay. So we need to find probability of B given A. We need to find probability of B given A. And B given A is equal to what? Probability of B intersection A upon probability of A. And we are given probability of A, but not probability of B intersection A. So with the help of this, we evaluate B intersection A. So first, probability of A given B is written as like probability of A intersection B. and probability of B. Okay. A probability of A given B equals 1 by 6, and probability of A intersection is like A intersection B, and probability of B is 1 by 4. So probability of A given B is what? Sorry, A intersection B, it's 1 by 6 into 1 by 4. Hello. Am I audible or not?
Yes, sir.
Yes, sir.
Yes, sir.
You are audible.
Okay, thank you. Okay, so we will calculate probability of A intersection B is this. So probability of B intersection is also the same. Na? One by 24. Now putting this in this formula, we get probability of B intersection A equals 1 by 24, and probability of B is what? It's 1 by 4. So it comes out to be okay. It's a mistake, na? It's 1 by 3, na? Probability of B given A 1 by 3. So it's 3 upon 24, which is equal to 1 by 8. Is it clear now? We want actually probability of B given A actually. Okay. So probability of B given A is B intersection A and A. And we don't know the value of B intersection A. So with the help of A given B, we first calculate the B intersection A or A intersection B. And then with the help of this, by this formula, we'll calculate the value. Okay. Okay. Now question number 4. For two events A1 and A2, if probability of A1 equal to this, probability of A2 equal to this, and A intersection B equal to this, then A and B are. Okay. Now the options are mutually exclusive and independent. Okay. All options are related to independent and mutually exclusive. Okay. Then for mutually exclusive, what? And for independent, we need to calculate for these two, na? Okay. Probability of A1 equals 2 by 3. Probability of A2 equals 3 by 8, and probability of A1 intersection A2 equals 1 by 4. Okay. So first for mutually exclusive. For mutually exclusive, what? A1 intersection A2 equal to, okay. For two events A1 and A2 are said to be mutually exclusive if A1 intersection A2 equal to 5. This implies probability of A1 intersection A2 equals 0. But here we are given probability of A1 intersection A2 equal to this. This implies not mutually exclusive. Okay. From here we say that this is not mutually exclusive actually. So that means this option and this option is not possible. Okay. Now we have either this or this, option C or option D. Okay. Now for independence. For independent event, probability of A1 intersection A2 must equal to probability of A1 into probability of A2. Okay, so probability of A1 is what? It's 2 by 3 into probability of A2 is it's 3 by 8. And from here, we get probability of A1 intersection A2 equal to 1 by 4. Okay, that means it is independent. That means option C is the right one. Okay, is it clear now? Okay, now next question. The odds that person X speaks the truth are 3:2, and the odds that person Y speaks the truth are 5:3. In what percentage of cases are they likely to contradict each other? It's likely to contradict each other on an identical point. Okay. So here we see that actually like odds in favor or odds against. There are two concepts, odds in favor or odds against. So here it is odds in favor. Like person X speaks truth 3 and not truth or lie 2 times. Okay, in a total of 5 times, he speaks 3 times truth and 2 times wrong, like lie. So that means probability that person X speaks truth equals 3 by 5. Okay, so person X speaks lie or false, that is it's 2 by 5. And for person Y as well, true, it is 5 by 8. And false, it is 3 by 8. In a total of 8 times, he speaks 5 times truth and 3 times false. Then probability of lie is 3 by 8 and probability of truth is 5 by 8. Okay. So our question is like in what percentage of cases they are likely to contradict each other? Okay. On an identical point. Okay. Then that means what? That means suppose it is the event E. Okay. So that means what? Like if person X speaks truth, then Y not and against. So for example, person X truth, okay, and intersection and Y false plus X false Y. Okay, okay. Here intersection term and comma both are the same thing actually. Okay, but for homogeneity, let me write intersection. Okay, so at a particular identical point, suppose X says the truth and Y says the false, and in the similar manner, X says false and Y says truth. Okay, so also we are also given that actually these two persons are independent by the nature of the problem. It is independent. Okay, so that means we can write probability that X speaks truth and probability that Y speaks false plus probability that X speak false and probability that Y speak truth. That means XT. That means 3 by 5 into YF. That is 8, 3 by 8 plus X given false 2 by 5, Y truth 5 by 8. And by solving, we will get 9 by 40 plus it's 10 by 40. That is 90 by 40. Okay, so the chances that they both are contradict each other on the same point is 19 upon 40. Means around 50% time they are opposite to each other. Okay. Okay, now question number 6. Here, 60% of the employees of the XYZ corporation are college graduates. Okay, of these 10% are in sales, 60% college graduates, and 10% are in sales. Then, of the employees who did not graduate from the college, 80% are sales. Then, what is the probability that an employee selected at random is in sales? Okay. Okay. So we define like events like this. First, we are graduates, we are sales. Two types of events are there. So, for example, let event A is defined like this. Like event A is employee is a college graduate. Okay, and also another event is like what? Sales. Employee is in sales. Okay, so what we need to actually evaluate, what is the probability that an employee selected at random is in sale? That means we need to find probability of B. Okay, and probability of B is what? Like when the person is graduate, 10% chances that he is in sale, and when it is not, he or she is not graduate, then it then 80% chances that he or she is in sales. Okay, so we need to consider both the scenarios. Okay, so first we are given probability of A. What is probability of employees in a college graduate? 60% are college graduate. So that means 60% are college graduate, or 0.6. Probability of A is what? 0.6. Probability of B is in sale. This is actually we need to calculate. Na? So it is. Okay. Now 10% are in sale. Like probability that B given A, we want the employees who is in sale given is college graduate. It is given that it is actually 10%. Okay, so that means 0.1. The probability of B given A is 0.1. Also, of the employees who did not graduate from the college, 80% are in sale. Okay, so probability that okay, we write here probability that the person is in sale given he is not college graduate. This is 0.8, 80%. Na? It is given na 60% of employees of XYZ corporation are graduate. So 60% are graduate. Of these, 10% are in sales. So B given A, B is in sales. So B given A is 10%. And of the employees who did not graduate, so probability of college graduate who are graduate is 60%. So probability that A complement, that those employees who has not graduate is 40%. So probability of B given A is given 10%, and probability of B given A not is 80%. All these things are given actually. Okay. Now we need to calculate probability of B. So probability of B is defined as how? Can anyone? These two scenarios, na? Like we can write like this, na? Okay. So it's B. The set B is what? The A intersection B part is this, and A complement intersection B part is this. Na? So we can write B as the A intersection B and A complement intersection B. Okay. Now, with the help of multiplication rule, we can write A intersection B and A complement intersection B, like probability of A, probability of B given A, plus probability of A complement, probability of B given A complement. Okay. And all these four probabilities are known. So from here, probability of A is what? Probability of A is 60%. Okay, 0.6 into probability of B given A is 0.1. Probability of A complement 0.4 into probability of B given A complement, it's 0.8. This equals 0.06 plus 0.32, which is equal to 0.38. So 38% chances that the employee selected at random is in sale. Is it clear or not? Or if there is some problem, you may ask. Na? Anyone?
Sir, can you explain it once again, please?
Okay. Okay. Let me rub them first. Just see. What is the question actually? 60% of the employees of XYZ Corporation, 60% employee of XYZ Corporation as college graduate. Okay. The first event is college graduate. The person may be college graduate, or it is not, or he or she is not college graduate. Okay. Then out of these college graduate students, 10% are in the sales. Okay. So those who are college graduate, 10% of those people work in the sales department, suppose. Okay. It is given there. Also, of the employees who did not graduate, also those who are not graduated from the college, 80% of them are in sales. Okay. We are given two conditions. Either they are college graduate or they are not college graduate. If they are college graduate, then what is the percentage that, what is the chances that he is in sales? And if he or she is not in college graduate, then what is the chances that he or she is in sales? So we are given 60% chance, 60% are college graduate, 40%, 60%, just a second. Okay, we are given 60% are college graduate and 40% are not college graduate. Okay, two cases. And if they are college graduate, the probability that he or she is in sales is 10%. And if he or she is not college graduate, then the probability that they are in sales is 80%. So we have a scenario. If we randomly choose a person, the first thing, either he or she is a college graduate or not. Okay. So in both the scenarios, if he or she is a college graduate, then he or she is in sales. So this and this. These two are what? A.
Okay.
Okay. Okay. This is actually college graduate and in sales. This is not in college graduate, not a college graduate and in sales. These two scenarios are arise only. This, okay. And this can be written with the help of multiplication rule, like this, and then, okay. Actually, in Bayes theorem, you say that in Bayes theorem, this is the denominator part for Bayes theorem. Suppose we may construct a question like this as well. Like if we select an employee and we found that that person is college graduate, then what is the probability that, let me frame again. Okay, suppose we frame the question like this, like suppose we select a person and he is in sale. Okay, and he is in sale, then what is the probability that that person is college graduate, or what is the probability that that person is not a college graduate? So this is the case of Bayesian probability. Okay.
Okay, sir. Clear. Clear.
Okay, then we have a question regarding that actually. Okay. Now, question 7: a die is thrown twice, and the sum of the number appears is observed to be 7. Then what is the conditional probability that the number 2 has appeared at least once? Okay. So if we roll a die 2 times, okay, then like sample space like this, no? It's 1, 2, it's 6, 6. Number of elements in sample space is 36. Is it? I think everyone know this. Okay. Now our aim is to find those elements whose sum is 7, because A, suppose we define A sum is 7. That means either 1, 6 or 2, 5 or 3, 4 or 4, 3 or 5, 2 or 6, 1. These are the 6 possible cases when we get 7 as an outcome. Okay, when we roll 2 die. Okay, now also we are given conditional probability that the number 2 has appeared. Okay, so event B, we may define event B as number 2 has appeared at least once. Okay, so actually from here you people see that now, since we are given conditional, we need to calculate probability that B given A. Okay, that number 2 has appeared given that it is 7. So it is what? Here 1, 2, and the total number is 6. 1 by 3. It is a direct approach, but we will use the formula. Okay, we'll use the formula. Okay, so for this A is this and B is what? The elements in B is it's 2, 5 and it's 5, 2. Now we need to calculate probability of B given A. That means probability of A intersection B divided by probability of A. Now the probability of now first A intersection B is what? A intersection B is actually okay. A intersection B is actually 2, 5. There is something mistake actually. Something is wrong here.
Sir, there is B
Yes.
is the event that 2 has appeared at least once.
Yes.
It does not mean that we take only 2, 5 or 5, 2.
Yes. Got it. Actually, at least once, na. So like it's 1, 2, it's 2, 1, it's 2, 2, up to it's 2, 6, then up 3, 2, then 4, 2, then 5, 2, and then at last 6, 2. These are the B, na. Like when we roll 2 die, so 2 has appeared at least once on either of the die or in both dice. So this is the possibility. Like 6 case is there, 7, 8, 9, 10, 11. 11 possibilities are there actually. Number of elements in this is 11. Okay, and A intersection B has 2 elements. Number of elements in A intersection B equals 2. Okay, so now the probability that B given A equals number of elements in A intersection B. Okay, let me write it directly. Okay, probability of A intersection B, that is 2 by 36, and probability of A, that is 6 by 36, which is equal to 2 by 6, which is equal to 1 by 3. Okay, I think it is clear, na?
Yes, sir.
Okay, question number 8. A lot contain 15 articles. A lot contains
Excuse me, sir. Can we
Yeah.
go over this question again, please?
Yes, sure. Okay. Okay. Let's take the question and understand. Okay, a die is thrown twice. Okay. Then when we throw a die or roll a die 2 times, then the possible outcomes are 1, 1, 1, 2, 1, 3 up to 6, 6. And the number of these outcomes are 36. Okay, is it clear?
Yes, sir. That's clear.
Okay. And now, what is the random variable defined? Sum of the number appeared is observed. Okay, sum of the number. And the sum of the number is 7. So when we discuss about sum of the number, it's from 2 to 12. But we have given the condition that let we define its event A. As event A, sum of the number is 7. Here is given. So out of that 36 outcomes, we want that pair that have 7 as a sum. So we get like 6, 1, 6, 2, 5, 3, 4, 4, 3, 5,
So
2, and
this
6.
is clear, sir.
Okay.
So this is clear, sir. What I'm having problem in, comprehending is in B, you have said that 2 has appeared at least once.
Yes.
Now, sir, when the overall set we are talking of is that 7 has been observed, isn't it the case?
No. That is not the case. No. We are actually event A and event B from the sample space. No? It is defined on the basis of sample space. First case, we will observe those pair that have 7, that have a sum 7. And the second is B. Event B is defined as 2 has appeared at least once. Then our question is like this: the conditional probability that the number 2 has appeared at least once. That means this conditional probability stands for like it is given that event A has already occurred. Okay, now we will focus on event A. Okay, the meaning of the question is like this.
So you're
Here
talking,
the
sir,
word
that these are two separate events. Event 1 was in which we had in the dice throw twice, we had 7 as the sum. That was one event.
Yes.
Now you're talking there's a second event that had that
Yes.
sum not been 7, or that 7 has got nothing to do with this B event, that only 2 has been appearing in one of those 2 dice throws.
Okay. Let me let me write the question again. Actually, the question is what like if the conditional is not there. Okay, then these are two different questions. The first is a event A is observing 7 as a sum, and event B, what is the probability that the number 2 has appeared at least once. Okay, but
Yes,
this
sir.
conditional word actually stands for what? That this the particular event A, which is already happened, then on that basis, what is the probability that the number 2 has appeared at least once? Okay, this conditional is stand for that actually. I have rubbed this conditional. If this conditional is not there, that is stand for that if event A has occurred, then our aim is to from that we need to focus on that event. Okay, now we have a this. Now we have this event A as a kind of modified sample space, for example. Okay, this
Okay,
conditional stands for this actually. Actually, you can write this question like this as well. Then what is the probability that the number B, like the number 2 has appeared at least once, given that event A has already occurred? This is the question actually. This conditional is stand for this question. Okay.
Sir, how
Yes.
is this event B related to event A then?
Because this is conditional, na? The conditional word is what?
So
Yes,
that
sir.
is understandable. Sample
Yes.
space, if we talk of, we have thrown the dice twice. It will include all the numbers that have come in both the dice throws. That is understandable. Now coming to a
Okay.
event A, we did a event A. Now event A will be part of that sample space only, sir.
Yes.
In that sample space, we have thrown the dice only twice. When we threw
Okay.
the dice 2 times, that means this is the number of that sum of 7 will be only these that you have given in the screen, sir.
Yes, sir. Event is.
Now,
Yes.
now, sir, we come to the event B. Now, event
Yes.
B will also be part of the event A only, sir, and part of the same sample space.
Actually, let's understand this. Actually, the meaning of this, na. Suppose, for example, I frame the question like this. Okay. Like the same question, number A, okay, number 7, and the probability that the number 2 has appeared at least once, given that event has already occurred. Okay.
Just, sir, for my understanding, sir,
Yes.
what we have calculated now, if B2 had appeared at least once. Now,
Yes.
in the total sample space, if we calculate if 2 has appeared once, will these both probabilities be same?
Okay. Can you ask again?
So, sir, I am
Last
saying,
part.
let's say in the same question, we threw a
Yes.
dice twice, then
Hmm.
then we saw that what is the possibility of event A happening. That is one question, sir.
Yes.
Then after that, we're saying B has happened in which 2 has appeared at least once.
Okay.
Now, if we forget this question and we only concentrate on we throw the dice 2 times, what is the probability of 2 coming?
Yes.
Will
That is
this question, what we are writing and the question that I asked, are they same, sir?
like here in like suppose omit this part. Okay, this part, and we throw a die twice. And what
Yes,
is
sir.
the probability that number 2 has appeared once? At least
Yes,
once.
sir.
At least once.
Yes, sir. At
So
least
that
once.
means yes. So that means what? That means B has this element, na? It has 11 elements.
Yes, sir. 11, sir.
11 elements. So the probability is what? It's
It is
11
11 by
upon
36, sir.
11 upon 36. Okay.
Yes, sir. Yes, sir.
This is the prior probability.
Yes, sir.
Okay, but we are discussing about the conditional probability. We are discussing about the conditional probability.
Sir.
And yes, and in conditional probability, we are given a suppose event A, given event B. Na, this is a condition na, that any event, this event already occurred. Then on the basis of that event, what is the probability of getting this event?
So that's precisely I'm saying. So that in one way, event B has to be a subset of event A.
Yes.
Sir, if
Actually,
that
event
be
first
sir.
of all, event B comes from the sample space. Na?
Yes, sir.
Suppose we are not given a conditional. We are not given a conditional probability. In that case, event A and event B are written like this, na? Like event A and event B. Okay.
Yes, sir. Yes,
But
sir.
now our aim is to evaluate the conditional probability. In
Yes,
that
sir.
case, in that case, we need this formula.
Yes, sir.
In that case, and in the here in numerator part, A intersection B. Now A intersection B is like this.
Yes, sir.
It is okay. So it is B given A. It is B given A, and it is B. So both are different.
Yes,
Na?
sir. So understood, sir.
Okay. If not, you may ask again. We will try to discuss. Na?
No, sir. Sir,
Okay.
initially when we were solving this problem, initially when you started, you wrote
Yes.
B as 2, 5, and 5, 2 only.
Yes. That was mistake. No? By mistake, actually.
No, no, no. Sir, I'm trying to understand that only, sir.
Okay.
Now we are saying A intersection B is 2, 5, and 5, 2.
Okay. Okay. Actually, suppose what I have written, like B equals 2, 5, and 5, 2. This is the
Yes, sir.
question.
Yes, sir.
Actually, this is what? This is actually what? P is 2 or 5 or 5, 2. It is not possible. It is only possible when we have A. A has already occurred. then it is possible, na?
Sir, in conditional probability, we are talking of this only. A has already occurred.
Yes.
What is the possibility of B occurring now? Now
Yes.
B
So-
occurring, sir.
Yes. Okay, let's see. Let me explain. Like here, this event B, it is only possible to occur when A has already occurred, na?
Yes, sir.
And this is written by like this: B given A. It is written B given A. It is a B given
Yes,
A
sir.
condition.
Yes, sir.
And we are rolling two dice or a dice twice. Both are same thing.
Yes, sir.
Okay. We are
Yes, sir.
rolling
One
two
is the same
dice.
thing. Sir.
Yes. So from there, this is not the right case. This is not the total possible outcomes for getting at least two once, getting two at least once. Okay, this
Sir.
is wrong thing actually. That is why this is wrong, because
No,
this
sir,
already
what?
consider this event B already considered that event A has occurred. So this is the
Yes, sir.
conditional. So this is the conditional. So we do not write this as event B.
No, so are we talking of then if we have thrown the dice 4 times? We threw the dice twice?
No. Okay. Just start from beginning. Okay. Let's
Yes, sir.
start from beginning. Like we roll a die twice. Okay.
Yes, sir.
So we
6 into
get
6,
one.
36, sir.
Yes. 6 into 6, 36 are there. Okay.
Yes, sir.
And
Yes, sir.
again, event A, that we get 7 as a sum.
Sum of
Okay.
7. Understood, sir.
Sum is 7. So there are 6 possibilities are there. Okay.
Yes, sir.
Event B is like at least 2. We get 2. Sorry, not it. We get number 2 at least once. So there are total 11 possibilities
Yes,
that
sir.
is written here. Okay. Now
Yes,
our
sir.
question is like this. Like this. It is conditional probability. That means conditional. That means ki like B at least once. 2 has occurred at least once. Given condition A has occurred. Now, when we are given condition, then we need to modify our sample space on the basis of that condition.
Okay, sir.
So the formula for this is A intersection B upon B. So now B is given there. Oh, I'm
Yes, sir.
writing it again. I'm writing it wrong. Okay, it's probability of A. Na? Okay.
Yes, sir.
So
Probability
A,
of A. Yes, sir.
okay. So A intersection B is the thing that we need to focus, and probability of A. We are not going to discuss about the whole sample space now because it is given conditional. Okay,
Sir.
we need to focus on the given condition. From that condition, what is the possibility to get this? Okay.
Sir.
First, it is independent, like not independent word
So,
actually. Like,
but
yes.
here, sir, if B was only 2, 5, and 5, 2 also, then also probability of A intersection B will remain the same because A intersection B will still be 2, 5, and 5, 2.
Okay, but how B is equal to 2, 5, and 5, 2 when we are our random experiment is what? Our random experiment is rolling die twice. Then 2, 5, and 5, 2 is not the case.
Yes, sir.
Then 2, 5, and 5, 2 is not the overall case. The first thing is this.
So
na?
not the
Like,
overall case. I'm only talking of case B. Overall case
yes.
understood. Sample
No,
space
actually,
understood.
no. Let me explain again. Actually, here B equals 2, 5, and 5, 2. It is not completely written. Na? What is B? What is the event B? Okay. Suppose
B.
I have removed this. Okay. These things. We roll a die twice and the number 2 has appeared at least once. Then what will you write?
Yes, sir.
We will write this. Na?
So then we will. Then we will write this, sir.
This.
That's
Okay.
11 by 36.
Okay. Okay. Then, and when will you write like this? When you have a condition, and that condition is A.
Yes,
Then we
sir.
write like this. Na? So we are already discussing about the conditional distribution or conditional probability.
So that is precisely I'm saying. We know this, that the 7 sum has come. Now
Yes.
in that 7 sum, how many times till do 2 appear?
Yes. This is
In
conditional.
that, so in that 7 times, 2 has appeared only twice.
Okay.
That is 2, 5 and 5, 2.
Yes.
That means it will be 2 events overall happening in that
Six.
7, sum 7
Six.
is total 6.
Yes.
So it will become 1 by 3 state, isn't it, sir?
Yes, I have already told this no here. Like, see this.
Yes.
I've already told this now from here, because we will visualize these na, A and B. So from here we will directly write this 1 by 3 or 2 by 6. It is clearly visible. But
Yes, sir.
with the from the process, we are given what? B given A. We are asking about the B given A. Then
Yes, sir.
it is written as A intersection B divided by A. That means A
So-
intersection B is what? When this is what? Okay, let me erase something. Okay, and this is what? Number of element in A intersection B divided by number of element in sample space.
Yes, sir. So sample
And
state will get cancelled out. That is understandable, sir.
exactly. So this is the formal way, no? Of total procedure like this. We can already say that, na? We can calculate
Sir,
with the help of this as well.
Sir, I have
What?
understood the complete process that you have given. Only doubt which
Okay.
I am not able to comprehend is when we talk of a conditional probability, so it is like a condition. Okay, sir, can you draw the Venn diagram for this?
Okay, let me try then. Should I draw like here? Okay, suppose this is 36 elements. Okay, and event A is like this, and event B is like this.
Roger, sir.
Okay. Now, our question is first we first
Sir, now understood, sir. Sir, I got it now. I have
okay,
got it, sir.
okay, got it. Okay,
So
then
basically, we are only talking about the A intersection B part. Total B we're talking is of 11 events, and whatever that number of event was there, sir, NB.
it's
This is
11.
total B when 2 has appeared in overall. And
Yes.
total A was the number of 7 events. And this
Okay,
overlap part is 2.
exactly. And
Sure. Got
you
it,
are
sir.
actually from here. Where is this? Here you said na, like this is the
Yes,
case.
sir.
This part overlap, like intersection part. Okay.
Understood, sir.
Okay then. Okay, now on the next question, a lot contain 15 articles, of which 4 are defective. 15 articles are there in the lot and 4 are defective. Then articles are taken one by one at random and examined. The examined article are not put back. Then what is the probability that the 9th article is the last one? Okay. Okay, we are given 15 articles. Okay, and out of those 15, 4 are defective. Okay, we need to examine whether those or we need to uh, examine those 4 defective items and separate it from those all the articles. Okay, and at the ninth uh, time, or at the ninth art examination time, we will get the 4th defective item, and the probability of this event we need to calculate. Okay. Okay, then how we will calculate this? Can anyone tell? Actually, okay, look, this is the case for a negative binomial distribution when we are going to discuss about the spatial cases, spatial discrete and continuous random variables. Then this question can also be solved with the help of that. But here, suppose at ninth draw, we need to find the fourth defective. Okay, the question says this, na? Like what is product? The ninth article examined the last. Means at ninth we get the fourth defective. Okay, so before ninth there are 8 possibilities. Okay, so probability that like ninth item is last. That means what? First 8 items, in the first 8 items there will be 3 defective items are there, na? So we can write like this, like probability that 3 defective in first 8 row. Okay, then probability that ninth draw is defective. Can we write like this, the same question? Or if anyone not able to understand, then ask. Can we write the same question like this, na? Like here there are 15 articles, out of which 4 are defective. We need to examine and the defective item are not put back. Okay, then first in the first 8 draw we need to find the 3 defective item, and at the ninth draw we need to find the last defective item, and I am writing the same thing. Okay, now what? 3 defective items in the first 8 draw. That means what? We are given 4 defective draws, out of which 3 are selected, and we are given 11 non-defective. 11 non-defective articles are there, and out of which how much we need to select? 5. Is it clear? Because in the first 8 draw, we need to find out 3 defective and 5 non-defective out of 4 defective and 11 non-defective. Okay, and the probabilities like out of 8, 3 are defective. That means out of 15, we need to draw 8 articles. Is it the case, na? For first case, for this scenario, this is the probability. If anyone have doubt, okay. And at last, since we are already checked 8 items and that there are total 15 items, then there are still 7 items are there. And out of these 7 items, there is 1 defective item. So this is the overall probability. Is it clear or not? We will discuss about it.
Can you explain one more thing?
Okay. Let me again explain it. Okay. See, just focus on the question. We are given 15 articles. Just a basic concept. We are given 15 articles, out of which 4 are defective. We need to find out those 4 defective items. Okay. For this, we will check all items one by one. Okay. Now at the ninth draw, we will find the fourth defective. The last defective item will be drawn at the ninth draw. Okay. So in that case, what? That means in 8th draw, we are able to find out the 3 defective items. Okay. So 3 defective items are drawn in first 8 draws. Okay. And it may possible that first, second, and third are defective, and then fourth is not defective, fifth is not defective, sixth is not defective, and 7 is not, and 8 is not. It may also possible 1, 2, and then third is not defective, fourth is not, fifth is defective. There are many cases actually. So all these cases like this. Okay. Out of 4, 3 defective are selected, and out of 11 non-defective, 5 non-defective need to be selected in the first 8 clause. And in a total of a total possibilities of a total possible ways, for total possible ways, we are 15 articles, and out of 15 we need to draw 8 articles. So there are 15 C8 ways to total ways actually. Okay, so this is the case. The probability is this. Now again, at the 9th draw, defective item is need to be drawn. Okay, for that we are still have 7 articles remaining, and in those 7 articles there is only 1 defective articles are there. So the probability of getting the defective article at the 9th draw is 1/7. So this is the overall probability. Okay. You may solve the answer. I think the answer is something. I don't know actually the answer is. Is it clear or not?
Yes, sir.
Okay, okay. Now, next question. For detecting a disease, a test gives a correct diagnosis with probability 0.99. Means 99% times the result gives the correct means it diagnoses the correct. Okay, and it is also known that 1% of the population suffers from the disease. Okay, if a randomly selected individual from the population test positive, then what is the probability that the selected individual actually has a disease? Okay, means that a person actually has a disease. So that means what? Here also again we need to. It is also a case of conditional probability actually. Okay, let's see how. For first, what we are given. We are given a test detecting the disease, a test. Test is correct diagnosis with probability this. Also the 1% population. So we are given 99%, 1%. These two are given. And test is positive and the individual has a disease. These two are the events that we are going to define. First, event A. Suppose event A is test is positive. And event B, or not B, it's like B1 or B2, or event B1 is what? Person has a disease. Okay, so what we need to calculate? Probability that what is the if a randomly selected individual from the population test positive, then what is the probability that the selected individual actually has a disease? Like probability of B1 given A, we need to calculate this, na? So it is a case of conditional distribution again. Okay, and we are given what? Probability of B given A is probability of B1 intersection A upon probability of A. Now, what are the values we are given? First, test for detecting a disease, a test gives correct diagnosis with probability 99%. Okay, so 99% of the time the test gives the correct result. That means if that person test positive, then it has a disease. Person has disease, then the test result gets positive is 0.99. It is given this. Also, it is known that 1% of the population has disease. That means probability of B1 equal to 0.01%. So B2 is what? That person. Okay, sorry. Probability of B2, that person has no disease, have not disease. That means that is 0.99. Okay. Also, we are also given one thing. what? That is probability that A given B2. Can anyone tell me what is the value of this? Probability of A given B2. Anyone? Okay, let me.
0.01.
Hello.
0.01.
0.01. Okay, how?
So the probability that A means the test is positive and B2 is
Okay.
has no disease. It means it
Yes.
gives wrong result.
Okay. Yes. Yes. Exactly. Exactly. Okay. See here, probability that A test positive, 99% of the time test gives the positive result, and that means 1% time it is gives the negative result. Means wrong result or incorrect result. So it is 0.01. Okay. Now the probability of B given A equal to probability of B1 intersection A upon probability of A. So probability of B1. Okay. Now how to proceed? Probability of B1 given A with the help of Bayes theorem, we can write it like this: probability of B1, probability of A given B1, and divided by probability of B1, probability of A given B1, in plus probability of B2, probability of A given B2. This is the Bayes formula. And now putting the values, we get probability of B1, which is equal to 0.01 into probability of A given B1, which is equal to 0.99, 0.01 into 0.99 plus probability of B2, 0.99 and 0.01. And this gives probability of B1 given A equals 0.5. Okay, anyone have doubt how these prior probabilities or conditional probabilities are given? Okay, next question then. An urn contains 6 white, 4 red balls. 6 white and 4 red balls. A ball is drawn randomly and put aside without noticing its color. The one more ball is drawn and it is white. What is the probability that the first ball is white? Okay. It's 6 white ball and 4 red balls. Okay. So initially we draw a ball randomly and we do not notice the color. Then at the second draw, the one more ball is drawn and it is white. That means the second ball is white. It is given. Then what is the probability that the first ball is white? Okay. Again, we have a same question. Like suppose we define A1 like this: the first ball. Okay, and A2. So first we need to consider like the first ball is either white or the first ball is red. Both the possibilities are there. Okay. And the probability of getting first ball as white is what? 6 by 10. There are total 6 balls, 6 white balls, and there are total 10 balls are there. At the first draw, getting a white ball is 6 by 10, or getting a red ball in the first draw is 4 by 10. Now, we need to define the likelihood like this. We are getting the second ball. Okay, second ball is white because it is given that the more ball is drawn and one ball and it is white. The second ball is white. Okay. So now we need to calculate what? So like probability that B given A1, probability that B given A2. There are two possibilities. Okay. So probability that the second ball is white, given that A1 has occurred, means the first ball is white. In that case, the second ball is what? It's 5 by 9. because the first ball is put aside, na? And white ball is removed from that box. So that means 5 by 9. And the probability that the second ball is white, given that the first ball is red, that means 6 by 9. Okay. Now the question is, okay, what is the probability that the first ball is white? That first ball is white, A1, given the second ball is white. We need to calculate this again with the help of Bayesian formula, Bayes theorem. Okay. It is written as like probability of B given A1 into probability of A1, and here probability of B. Probability of B is the summation of the B given A1 into A1 plus B given A2 into A2. Okay, so it is 5 by 9 into it's 6 by 10. It's 5 by 9 into 6 by 10 plus probability of B given A2, that is 6 by 9 into probability of A2, that is 4 by 10. So it is 30 upon 90, and it is 30 upon 90 plus 24 upon 90. So 90 is cancel out. So this gives 30 upon 54, which is equal to 6 5 6 9 5 by 9. Okay. Now next question. Let A and B are two independent events with probability of A plus probability of B equal to 1, and probability of A intersection B is 2 by 9. Also, if A probability of A is less than probability of B, then what is the value of probability of A? Okay. So for this, okay, so we are given first like this, na? Like probability of A plus probability of B equals 1. It is given there. Okay. Also, the events are independent. So that means probability of A intersection B equals probability of A into probability of B. Okay. And probability of A intersection B is given as 2 by 9. So that means it is probability of A into probability of B. From here, we can write probability of A equal to 1 minus probability of B, or probability of B equal to 1 minus probability of A. We can write like this. Okay. So for suppose we can write like this, probability of A into probability of B can be written as 1 minus probability of A. Okay. Now it is 2 by 9. It's probability of A minus probability of A square. It is the equation now. We need to solve this equation. Suppose probability of A equals small p. Okay. Then this equation is what? P square minus P plus 2 by 9 equals 0. Or we can write 9p square minus 9p plus 2 equals 0. Now we can okay, 9p square minus okay, 3, okay, 6 plus 3p plus 2 equal to 0. This implies from here we get 3 So 3p. So 3p minus 2 and plus 1, it's 3p minus 2 is minus. And from here 3p minus 2 is taking as common, 3p minus 1. This implies p equals either 2 by 3 or p equals 1 by 3. Okay, so probability of a equals p, suppose we get this, so probability of a equals either 2 by 3 or 1 by 3, and here we are given that if probability of a is less than probability of b, that means probability of a equals 1 by 3. Okay, is it clear?
Yes, sir.
Okay, now next question is 12. 4 balls are put at random in 3 boxes. Okay, what is the probability that the second box will remain empty? Okay, suppose we are given 4 boxes. 4 balls are put. Oh, okay, sorry, 3 boxes are there actually. Okay, suppose we are 3 boxes and we need to put 4 boxes in these 3. So the total number of possible ways to put 4 boxes in 3 boxes. 4 balls in 3 boxes is what? 3 to the power 4. Because we may put all 4 balls here, or 2 here, 1 here, 1 here, or 3 here, 1 here, 3 here, 1 here, as like. So there are 3 to the power 4 possibilities. Okay, like first ball have 3 options, second ball have 3 options, third ball have 3 options, and fourth ball have 3 options. So this implies 3 to the power 4 possible ways. Now there is a condition. What is the probability that the second box will remain empty? Okay, so in that case, when second ball is remain empty, that means we that box. Na? For example, we remove that box. Now we have only 2 boxes, and we need to put all the 4 balls in this. So again, the favorable case, the total favorable case is what? We can put all the 4 balls in second, means like first ball have 2 options, second ball have 2 options, third have 2 options, and fourth
2 to the power 4.
2 to the power 4. So it is simple, like the probability that the second box will remain empty is what? 2 to the power 4 upon 3 to the power 4. That is equals, we may write like this, 81. Okay. Okay, this is which of the following statements are correct with regards to the CDF of a random variable?
So
it is monotone.
can we
Yes,
go back once?
yes.
Okay, 2 to 2. Understood,
Actually,
sir. Thank you, sir. Got it, sir.
okay. Now, question number 13 is which of the following statements are correct with regards to the CDF of a random variable x? Okay. When x is a random variable, then which of the following is the correct for a function to be a CDF? So it is a monotonic increasing function. Actually, it is a definition. Yes, it is a monotonic increasing function. And also the value at minus infinity is 0 and at plus infinity or maximum value is 1. It is also the case. And it is continuous function of x from the right. It is also true. It is the property that we are discussing. Then what a function to be a CDF, a cumulative distribution function. So all these 3 are actually correct. Okay. Like fx is defined as this. So it is monotonic increasing or monotonic non-decreasing actually. Okay. So it is the first condition apply. For second condition, you may also like this. If you want to like Okay, this is the property actually. Okay, if want proof, maybe sir has already covered this in lecture. Okay, so all the three options are correct actually. Okay, we'll go for the next question.
One question, sir.
Yes.
If it is strictly increasing, then
Where?
if it is strictly monotone increasing.
It is monotonic increasing, like monotonic, not like of. Okay. We will solve question number 14. I think you got the answer, your answer, what you've asked.
Okay,
Because
thank
it is the question. Suppose we are given a function f from R to R, be a function which one of the following is not a CDF. Okay. So for a function to be a CDF, all these three must hold. Okay. So let's start with the function first. We are given fx equals 0 when x is less than or equal to 0, x by a and a and 1 for x is greater than or equal to a. Okay. Now first we will check these three property. Is this all the three property holds? If yes, then this fx is said to be a CDF and otherwise not. So for first let like okay. Suppose we have take x1 and x2, two numbers. Okay, two where like x1 is less than or equal to x2, we may say. Okay, so in that case, f of x1 is what? It is also greater than 0. Okay. In that case, fx1 is what? It's x1 upon a. And f of x2 is what? It's x2 upon a. Okay. From here, since x1 is less than x2 and a is a positive quantity na, here, because from here we see that a is a positive quantity. That means like we can write like this: f of x1, f of x2. That means our second condition, non-decreasing condition, holds. Okay, either increasing or non-decreasing. So this function a is non-decreasing. Okay. Now in second case, what? Like a limit. Suppose second case, like if we take limit x tends to minus infinity. At minus infinity, we will get this. We will get 0 at x is equal to minus infinity from the defined function. Here, x is less than or equal to 0. We get the function value is 0. Okay. And also for limit x tends to plus infinity. And here, a may be any constant value, na? Then x is greater than equal to infinity, we will get the function value is equal to 1. So this condition also holds, na? Second condition. Is it clear, na?
Yes, sir.
Okay. And now the third limit, right continuity. For right continuity, we will write like this. We will write like this, like a limit x tends to, for right side continuity, at x is equal to 0, we will check first. Okay. At x is equal to 0, we will get fx equals, it's a 0 by a equals 0. Okay, for right continuity, from here we see that here 0 positive is what? We get to 0 from the positive side. That means it lies in the this case. Okay, so that means x by a, and x tends to 0. Okay, or we can also write like limit h tends to 0 f of x plus h at x is equal to 0. So it is what? 0 upon a, which is equal to 0. Okay, and the function value at x is equal to 0 is what? And the function value at x equal to 0 is 0. That means the function is continuous to the right, or it is right continuous at x is equal to 0. Again, also because we have two jump points here, na? One is 0 and another is a. We will also do the same for at x is equal to a. And we will check the same thing again, at x is equal to a, limit h tends to 0 f of x plus h at x is equal to a is equal to a upon a, because it is what? X upon a. Okay, so this comes out to be 1. And okay, I think no, it is right, I think. No, is it right? No? And the function value at x is equal to a is 1. It is given here. So it is right continuous as at x is equal to a as well. So it follows all the three properties. So that means the given function fx is a proper CDF. Okay. Hello.
Yes, sir.
Okay. Is it clear, na? Similarly, you may check for function b, for c, and for d as well. Okay. You will find it is a CDF. Okay. I think it is also a CDF or not. You may check whether it is a CDF or not. Option C is actually it is a CDF because it is a CDF for x exponential distribution with 1 degree of freedom. Sorry, 1 parameter. Okay, that's why I've known this. Okay, so this is it actually. Anyone wants to ask any question regarding any questions?
Sure. My question is from question number 13.
13, okay.
Yes. If option number first, if we replace it increasing by strictly increasing, then what?
Increasing by strictly increasing, okay.
Yeah. Then what?
It is also valid, na? Because okay, like the given function is monotonically increasing. Okay, like function value is actually wait, monotonically increasing. Strictly increasing is what? Like this symbol, na? Hello.
Yes, sir.
Yes, strictly increasing is there is no equality sign, na? So when
Yes, sir.
actually
Yes,
when,
exactly.
when we are saying increasing, that it includes strictly increasing, na? So it is also possible. For equality condition, for in case of actually uniform distribution, this equality condition gives, na? For a curve of uniform distribution like this, and the PDF is like this, and the CDF okay. Like you know about uniform distribution or not first? Hello,
Yes, sir.
do you know about the uniform distribution?
Yes, sir.
Okay, so the PDF
Okay.
of uniform distribution
Okay.
like this, na? And the CDF is if we are taking about 0 to 1 in case of AB, then it is 90°. So can we say? I think we can say it is also true for increasing or non-decreasing or strictly increasing both. Okay. For general, we will say that it is non-decreasing in nature. That means equal to sign is also there. Okay. And this is
Okay,
the
sir.
proper.
Thank you. Got it.
Okay. Okay. Anyone else? Okay then. Let me stop the recording first.